For a long time, AI progress looked simple. Bigger models, more data, longer context windows. And on paper, it felt inevitable. Just keep scaling and intelligence would eventually fall out. But quietly, across research labs, factories, and real-world deployments, that assumption is starting to break. Not because models stopped improving, but because people realized they were solving the wrong problem. The issue was never just how much information an AI could hold. It was how that information was handled. We assumed intelligence meant reading everything, remembering everything, and generating everything step by step. That turns out to be incredibly inefficient. Let's start with context windows. Over the past few years, they exploded in size. 8,000 tokens became 32,000, then 100,000. Then suddenly, million token models were on the table. The idea was simple. If the model can see everything, it won't forget anything. But in real use, the opposite happened. As inputs got longer, answers became fuzzier, costs went up fast, and performance dropped, especially on complex tasks. Researchers now openly call this problem context rot. The model doesn't fail because the context is too small. It fails because it's forced to process everything at once. Real intelligence doesn't work like that. Humans don't read entire books before answering a question. We skim, we search, we jump back and forth. We focus only on what matters. So newer AI systems stopped trying to store the world in memory. Instead, they started learning how to navigate it. Rather than loading massive prompts into a model's head, the information lives outside the model, like a workspace. The AI explores it step by step. It searches. It pulls small pieces. It takes notes. It delegates subtasks to smaller helper models. The model stops asking, "How much can I remember?" and starts asking, "What do I need next?" That single shift changes everything. Suddenly, input size stops being the bottleneck. What matters instead is how intelligently the system moves through information. At the same time, a similar realization hit multimodal AI. Most vision language models still work the same way. They look at an image or video, then translate what they see into text one token at a time. But language is messy. Multiple sentences can describe the same event perfectly, yet look completely different to a model. So during training, a massive amount of effort goes into learning phrasing, grammar, and word choice. Even though none of that changes the meaning, that's wasted work. Newer systems skip that layer entirely. Instead of predicting words, they predict meaning directly. They operate in embedding space, continuous representations that capture semantics, not surface language. Similar answers naturally cluster together. Different answers stay far apart. The model no longer has to guess how something should be said. It only needs to understand what it means. This has huge consequences. Inference becomes faster, latency drops, and real-time understanding becomes possible. Instead of waiting for text to finish generating, the system already knows what's happening. That's why video understanding, robotics, and perception-heavy AI are suddenly accelerating at the same time. Now, look at robotics. For years, the industry chased human imitation. 2 legs, 2 arms, perfect balance. But real deployment doesn't care about imitation. It cares about output. So the most effective robots today don't look the most human. They're built for efficiency. Wheels instead of legs, extra arms instead of symmetry, modular parts instead of biological realism. These robots aren't trying to look human. They're trying to work. And they are. Factories are already testing robots that outperform humans on changeovers and assembly tasks. Not someday, now. At the same time, humanoid robots are learning to walk in days instead of years, not because hardware suddenly improved, but because training moved into simulation. Millions of seconds of experience are compressed into virtual environments. By the time the robot touches the real world, it already knows how to move. The intelligence arrives before the body. And this same pattern shows up when AI crosses into physical creation. When spoken intent is translated directly into structured meaning, turning that into a physical object becomes a pipeline problem. Speech becomes design. Design becomes geometry. Geometry becomes fabrication. No manual translation required. This is how AI moves from screens into the real world, quietly, through structure. Even public infrastructure is changing. Traffic robots aren't chatbots with arms. They're systems. They read signals, synchronize with lights, detect violations, adapt behavior in real time. No dialogue required. No language-first reasoning. reasoning, just perception, coordination, and action. Across all of this, the pattern is the same. Intelligence is no longer centralized inside a single model. It's distributed across external environments, semantic representations, helper models, simulation. The core system stays focused on decisions, not overload. This is why scaling feels different now. For a long time, progress meant training bigger models with more data. Now, progress happens at inference time. By reorganizing how intelligence works, not just how big it is. The limit is no longer the context window. It's how well the system can navigate information that lives outside it. In computer science, this idea isn't new. Out-of-core algorithms process datasets larger than memory by carefully managing what gets loaded and when. AI is finally doing the same thing. Small working memory, massive external structure, meaning over language, navigation over memorization. That's why these changes feel subtle but irreversible. They don't look like upgrades. They look like foundations. And once intelligence stops living entirely inside a prompt, scale stops being the main constraint. That's the shift we're watching right now. If this helped you see what's really changing under the hood, you know what to do. I'll see you in the next one.